Okay, let's do another example and let's make it a bit difficult and let's consider conduction in a radial system or a cylinder. So let's say we have a hollow cylinder and sometimes it's also called as an annulus. So in the textbook or in some of the problems, if you see the word annulus, it means a hollow cylinder. And let's say the assumptions that are given are that there is no heat generation. There is and steady state conditions exist. And this is how the uh, problem looks like. So you have a hollow cylinder with an inner radius of R1, outer radius R2, and a fluid or the surface inside the hollow cylinder is at a temperature Ts1 and the surface outside at radius R2 is at temperature Ts2. Let's assume that there's a hot fluid flowing inside and the hot fluid is at a temperature T infinity 1 and the heat transfer coefficient is H1 and there's a cold fluid flowing over the cylinder, the temperature of which is T infinity 2 and the thermal conductivity is H2. So if we draw a circuit diagram for this problem, our heat will be flowing, let's write this down, our heat will be flowing in radial direction. So we will just have a QR. So it's still a one-dimensional problem, but our heat is now flowing in the radial direction and our circuit diagram will have a resistance due to convection which is due to the hot fluid inside, and the formula for this is 1 upon HA. But you must note that the area here is 2 pi RL, which is the surface area of the cylinder. Now because the heat is flowing in the radial direction, the area perpendicular to the direction of heat is the surface area of the cylinder and the uh, not the cross-sectional area. So that's why our area of interest here is 2 pi r1l and not pi r square. So this is wrong. Uh, Moving on to the resistance due to conduction, it will be a log of R2 by R1 which upon 2 pi KL. This is R conduction and this is something that we will be deriving in this particular example. So that is the motivation of this problem and then R due to convection again. So we have three resistances and they are in series. So let's begin with this problem and let's take a small control volume and let's say our control volume is something like this, which you can see here, the magnified view of the control volume. Uh, let's say that the temperature at some distance r from the center is Tr. The inner radius is R1, outer radius is R2, and we know the surface temperatures. So using the energy equation, we know that in the radial coordinates we can write the temperature difference or the differential equation of temperature varying with radius as this. Because we don't have any heat generation, our right hand side will be 0 and it's a steady state, so we don't have any time dependent terms as well. Now, to find the temperature distribution, our first step will be to integrate equation 1. So we'll separate variables and integrate. And before doing that, let's apply Fourier's law, or let's look at Fourier's law for in radial direction. So before we separate this and integrate, what we'll do is we'll look at the Fourier's law. So Fourier's law in radial direction will be QR equals to minus kappa time k times A into dt by dr, where your A is 2 pi RL. Okay, that's the surface area of the cylinder. So your QR will be minus k times 2 pi RL into dt by dr, and let's say this is equation 2. Okay, now why we looked at why we looked at Fourier's law first is because if you look at equation 1, or the heat diffusion equation, what we see is that uh, the second order derivative of temperature is equal to 0. Now what this implies is that if you integrate this once, this implies that your term in this bracket right here is constant. So implies that your kr into dt by dr term is constant, right? So that means that if you go back to the Fourier's law, we can write this as minus 2 pi L into kr times dt by dr. So this particular quantity is constant, which means that heat flux, which means heat flux is constant in the radial direction. And it's important that it's constant in the radial direction. And we proved that using Fourier's law and the energy equation. So let's uh, let's now move on to integrating and finding out the temperature variation with respect to radius. Okay, so let's use separation of variables and integrate equation 1, and keep in mind that this term here is a non-linear term. So we've seen in chapter 2 that after integrating this equation, the general form of temperature distribution that we get is C1 into natural log of R plus C2, where C1 and C2 are constants of integration. Now because we have two constants, we need two boundary conditions, and the boundary conditions that we have in this case are, we know the temperatures at R1, which is TS1, and we know the temperature at R2, which is TS2. So let's apply these boundary conditions. Uh, the two equations that we'll get is TR1 will be equal to C1 into natural log of R1 plus C2 equals TS1 let's say this is equation 3, and Tr2 equals C1 into natural log of R2 plus C2 equals Ts2. Let's say this is equation 4. Now let's do the operation of subtracting 4 from 3. So let's do 3 minus 4, which will give us C1 times natural log of R1 minus natural log of R2, and we'll cancel out C2's, so that will be 0 equals Ts1 minus Ts2. We can also write this as C1 into natural log of R1 by R2 equals Ts1 minus Ts2, or your C1 will be equal to Ts1 minus Ts2 divided by natural log of R1 by R2. Okay, now substituting this in say equation 3. So let's substitute this value of C1 in equation 3. Okay, so let's do it here. So after substituting in equation 3, we get Ts1 equals to, now the value of C1 is Ts1 minus Ts2 upon log of R1 by R2. That's your C1 times natural log of R1 plus C2. So we take this term on the left hand side, and we get C2 as Ts1 minus Ts1 minus Ts2 divided by log of R2 by R1 by R2 into natural log of R1, and we can simplify, and let's see if I can simplify this. No, so let's just leave it like this. So we got our two variables C1 and C2. Now we'll use them in our original equation, which was equation 2. Let's say this was equation 2. On substituting it in equation 2, we get, let's use a different color, just this. So we get our temperature difference, temperature distribution in terms of R as Ts1 minus Ts2 divided by the natural log of R1 by R2 into the natural log of R, which is the variable unknown, upon R1, which is known, R. Yes, so ln of R by R1, which is known, plus Ts1. Okay, so let's just check if our equation is correct. So if we substitute R equal to R1, we should get temperature Ts1. So if we substitute R equal to R1, this term will be 1 R upon, so it will be R1 by R1, and natural log of 1 is 0, so we get we get our temperature equal to TS1, which checks out. Let's see if let's see what we get if we put R equal to R2. So if we put R equal to R2, our denominator and numerator cancel out, but we'll get a negative term because this will be R2 by R1, but in the denominator we have R1 by R2, so we'll have a negative sign. And the negative sign, after pulling out the negative sign, the TS1s will cancel out and we will get temperature equals to TS2. So what I want you to do is I want you to make the substitution by yourself. So use the C1 and C2 that you've got here, substitute in 3 and see if you get this equation, and see what happens if you substitute C1 and C2 in equation 4 instead. So you'll get a slightly different equation, but it will still be a correct equation and it will still check out. So please do that for yourself, and keep in mind that this is a logarithmic equation and it's non-linear, unlike the plane wall case. Okay, so now let's take the temperature distribution that we've got and let's substitute it in the Taylor series. I'm sorry, in the Fourier's law that we have. So substitute, let's say this is equation 5. Substitute equation 5 into Fourier's law. After substituting that into Fourier's law, we get the heat heat transfer rate in radial direction as 2 pi into L into K multiplied by the temperature difference Ts1 minus Ts2 divided by the natural log of R2 by R1. Let's say this is equation 6. So this will be our heat transfer rate in the radial direction for an annulus or a hollow cylinder, and as you see it does not depend on radius. The radii R1 and R2 that you see here are known quantities, so they are numbers. You don't have a variable R here. So uh, if we have to define a thermal resistance in this case, the definition, as we know, will be R equals to delta T by QR, which will be Ts1 minus Ts2 divided by 2 pi L into the thermal conductivity multiplied by Ts1 minus Ts2. And I know that you're already looking at terms being cancelled out. So our temperature difference or the delta T's cancel out, and the thermal conductivity for for an annulus due to conduction is ln of R2 by R1 divided by 2 pi L into K. So if you get a problem where you have a thermal resistance or one of your thermal resistances is due to conduction through an annulus or a hollow cylinder, you will have to represent your thermal resistance by using this formula that we've derived right now.